Okay, so how do you study something that's literally billions of times smaller than anything you can see? And I don't just mean seeing it as a dot. I mean, how do you understand its actual shape in 3D? Well, today we're diving into this incredible technique that basically gives scientists a geologist toolkit for the nano world, and it all kicks off with a really simple but super powerful idea.
The folks behind this breakthrough pose this really cool thought experiment. Just imagine, what if a tiny nanocrystal, just 10 nanometers across, suddenly appeared in your hand as a 10-centimeter rock? You could turn it over, right? You'd see all its little faces, how the light bounces off of it. You'd get its structure instantly. And that is the goal, to become, for all intents and purposes, a nanogeologist.
All right, section 1, a geologist for nanocrystals. Now, obviously, we can't actually just scale up a nanocrystal like that, which brings us to the real problem, the fundamental challenge here. How in the world do you map a mountain that you can't even see, much less hold in your hand?
And that leads us right into section 2, seeing in 3 dimensions. To really get why this new way is such a big deal, we have to talk about how scientists used to do this. It really required a huge conceptual leap, almost like they went from trying to understand something by its shadow to just looking right at.
So the old method, which has this fancy name, reciprocal space analysis, it's kind of like you're in a dark room with a weird animal and all you have is a flashlight. You're trying to figure out what it is just by looking at its crazy, distorted shadow on the wall. I mean, you can do it, it's powerful stuff, but it's totally indirect. This new method, though, it's all about direct space imaging. It's like someone just flips on the lights in the room. You can just look at the animal. Way more intuitive, right?
So, how did they pull it off? This is the aha moment, and it's so clever because it's so simple. They basically asked, what if we could give one of the most powerful tools in science, the transmission electron microscope? What if we could give it stereo vision? Think about it. Your two eyes each see a slightly different 2D image, and your brain stitches them together into one 3D world. They wondered, could we do that, but for a tiny, tiny nanocrystal?
And their answer to that question brings us to section 3, the 2-tilt test. It's this simple but totally brilliant little procedure they came up with to create that 3D view. Let me show you how it works.
Okay, here's the game plan, and it's beautifully simple. Step 1, you take a super high-res picture of the nanocrystal. The goal is to see the atomic patterns, the lattices, from at least 2 different directions. Step 2, you tilt the crystal, and it has to be a very precise tilt. Step 3, snap another picture. And finally, step 4, you take the information from both pictures, do a little bit of geometry, and bam, you calculate the entire 3D structure.
All right, let's walk through what they actually did in the lab. They started with a nanocrystal of tungsten carbide. They get this first high-res image, and you can clearly see 2 different sets of lines, these lattice planes. So that's great. They've got 2 dimensions locked down. But the key ingredient, that 3rd dimension, is still hiding.
And then comes the most important part, the tilt. They rotated this tiny little crystal exactly 35.3 degrees. Now that is not a random number. They did the math. For this specific type of crystal, that was the magic number. The precise angle they needed to get a hidden 3rd pattern to pop out and show itself. I mean, the whole experiment, everything, rides on this one single precise move.
And guess what? It worked perfectly. After that tilt, a brand new 3rd pattern just snaps into view, one that you couldn't see at all in the first picture. This is the key. This is the missing piece of the puzzle. It provides the depth, the z-axis, if you will, that the first flat image just didn't have.
Now, there's a sciencey term for this. It's called non-coplanar. All that means is that the 3 patterns aren't all lying flat on the same surface. And once you have 3 patterns that aren't on the same plane, well, that's basically the geometric equivalent of having length, width, and height. All of a sudden, you have everything you need. You've got all the data to map out the crystal's entire 3D shape.
Which brings us to section 4, proving the method. Okay, so it's a beautiful idea in theory, right? But the real question, the one that really matters is, did it actually work? How good was this 2-tilt test
when the rubber met the road.
First off, let's just take a second to appreciate how hard this was. Because of the way their microscope was built, they couldn't just grab any old crystal and tilt it however they wanted. Nope. They had to find one that was already sitting in almost the perfect starting position. And the odds of finding one like that just by chance? About 1 in 2,000. So this wasn't some quick and easy thing. They had to patiently hunt and hunt and hunt for the perfect specimen.
Okay, so here it is, the moment of truth. They took their data from those two images and calculated a really important property of the crystal. It's called the lattice parameter A, which is just the size of its basic repeating building block. The big question was, how would their number from this new simple method compare to the official gold standard value you find in textbooks?
So the established textbook value, the number they were trying to hit, is 0.425 nanometers. That's the benchmark. It's a number that's been confirmed over decades using all sorts of different, much more complicated experiments. And the result from their two-tilt test, get this, 0.424 nanometers. That's an error of less than 1.3%. It's just incredibly accurate. It was the proof. They had shown, without a doubt, that you could figure out the complete 3D structure of a single nanocrystal from just two simple pictures.
I love how the authors put it in their paper. They just say, the experimental results were unambiguous. That's it. It says it all. Their whole nanogeologist idea wasn't just a neat thought experiment anymore, it was a real, proven, practical, and super powerful new tool for science.
And that success brings us to our final section, unlocking the nano world. Because look, this is way bigger than just one little tungsten carbide crystal. This technique has massive implications for how we're going to discover and engineer the materials of the future.
So why should you care? Why does all this matter? Well, because a material's 3D atomic structure, that's what defines pretty much everything about it. Its strength, its conductivity, its reactivity, the whole shebang. So if you can see and measure that structure directly and easily, you can supercharge the development of new materials. We're talking about stuff for smaller, faster electronics, creating smarter drug delivery systems for medicine, and designing way better catalysts for everything from clean energy to making, well, almost everything.
What this method really does is it lets us, for the first time, metaphorically hold a nanocrystal in our hand. We get to see it in the round. It brings this bizarre, invisible nanoworld into our familiar three-dimensional reality. And that just leaves us with one big, exciting question. Now that we can finally see them properly, what other secrets is the nanoworld about to give up?